Welcome to this pre-recording of lecture 14 of MCS 320 on symbolic computation. So the short title is Substitution, Expansion and Factorization. The longer title is the manipulation of symbolic expressions by substitution, expansion and factorization. So in the previous lecture we looked at the data structures, the structure on how expressions consists of operators and operands. So today we look into the three most important tools to manipulate expressions. So we want to manipulate expressions. Another way to say this is to rewrite expressions, making them simpler. For example, here we look at the expression at the left, and if we put it onto a common denominator, then the expression looks a lot simpler. Now, in doing this operation, one wants to avoid expanding the numerator. So one way to do this is to shield the x plus y from expanding by replacing it by another letter. So in some sense, one can also look at this expression for an efficient evaluation, and if you want to evaluate efficiently, then you would do the sum x plus y only once. So this could also be an algorithm for evaluating this expression better. So, but the point is, substitution is one of the most important operations on expressions. We distinguish three types of substitution. So the first one is called simultaneous substitution, where we replace all the variables or everything all at once. So if we want to replace A by B, B by C, C by A, then we substitute this, and that leads to a circular rewrite of the variables in the expression. So instead of a plus 2b plus 3c, we have b plus 2c plus 3a. So all the substitutions happened at once. So this type of substitution is, for example, interesting if you want to check if your if your expression is invariant under a change of variables. So symmetry is often a very important property in mathematics. So doing substitutions like these are interesting for other reasons. So one alternatively, the alternative to the simultaneous substitution is that you would replace A by B. You do this first, then you have B plus 2B sitting in the expression, and that gets simplified to 3B. If one then replaces B by C, then the 3C is added to the 3C, and finally one replaces the C by A. So if you see the substitution, then it's important to realize that often you want a simultaneous substitution, but be careful that what gets executed is not the sequential substitution. The third type of substitution is purely syntactical. And that operates on the string representation. So this is purely Python-esque. So one can take the string representation of the expression. For example, one can slice it. Suppose that you have a numerator and a denominator, and you want to substitute only, you want to operate only on the numerator, then you would only operate on the slice that represents the numerator. Another application is where you want to replace a variable by a symbol, but you want to do this very locally. And actually, the string representation is, in some sense, the most powerful one. You can replace any character in the string. But we will not do this much. In some sense, the syntactical substitution is kind of the lowest level substitution, and it should be avoided because you actually are no longer respecting the mathematical structure. So first half of this lecture is on substitution because it's important. So we will see a couple of applications when we go to SageMath. The other operation is expansion. So we have already covered or defined what is expression swell. So this happens in an exact computation when the size of the expression grows exponentially. So therefore, the expansion often does not happen automatically. But for example, this product here, you may want to collect the terms. So you may want to see this as a polynomial in X, where the coefficients are expressions in A, B, and C. So here we still have the common expression. And the partial expansion or the term collection here allows you to see this. So we have already covered this when we looked into multivariate polynomials, and that's actually the shortest answer to this. But with the substitution, we can prevent that A plus B plus C gets expanded when we expand the entire expression. So after the expanding, where the z gets in front of every monomial, we then substitute the z back into the a plus b plus c. So it's actually the same trick that we did in the first problem when we put things under the same common denominator. The last topic is the numeric exact and the symbolic factorization. Here I want to emphasize the typecasting. So every object has a class, so belongs to a class, is an instance of a class, if you like, in the object-oriented terminology. What we do when we look at the numerical factorization, we cast our polynomial into the polynomials with complex numbers. So the coefficients are cast into complex numbers. In the exact factorization, we keep on working with the same type of coefficients. And symbolically, we cast the polynomials, the coefficients of the polynomials, into the extended coefficient field. So there, the outcome of the factorization depends on the context. So we are going to apply the factor method on the object. If the object is belonging to the space of complex polynomials, then we execute the numerical factorization. And the numerical factorization is always approximate because we cannot represent the entire complex numbers exactly. When we think of exact arithmetic, we by default would think over the rational numbers, but the integers, finite fields, are special cases of these exact factorizations. The symbolic factorization always starts with irreducible factors that are obtained from an exact factorization. Okay, so this is already lecture 14, very close to the first midterm. So we have already almost covered half of the course. In some sense, the concepts that we are seeing, there starts to be some repetition here. So I defined numeric, exact, and symbolic factorization earlier. But here, just because the symbolic representation of numbers, in particular algebraic numbers, was important in the first part. When dealing with polynomials, one has to define the coefficient type. When talking about factorization, one has to talk about the context. So what are the type of the object the factor is applied to. Okay, so in this first 11 minutes I explained the essential concepts. Let's now move to the Jupyter notebook. So I have prepared the Jupyter notebook, and here you see the beginning problem. So let me swap the endpoint. So here is our problem again. We want to rewrite an expression, and we want to make it actually nicer. We want to make it simpler. So I have a worked worksheet, a completely elaborated notebook. In this recording, I'm going to make a new notebook, the one that I'm using for this recording. And this has the benefit that you can see me step by step building up the arguments, building up the examples. So in this lecture 14 of MCS 320, we manipulate expressions with the substitute, expand, and factor methods. So let me start to begin with the substitution. So we have already covered substitution when it came to the evaluation, the symbolic evaluation. So symbolic expressions, we can evaluate them symbolically by replacing the variables by expressions. With substitutions, we are able to substitute or to replace expressions in an expression by other symbols or expressions. So that's the more general nature of the substitution. So what do we want to do? Here is the example. Our problem is to rewrite, and if you learn some LaTeX along the way in this course, this is a good thing. So I have my sum that I want to bring under common denominator. So I'm using the $$ to have it very nicely formatted in an environment. Now so this is symbolic computation, and what I really want to avoid is expressions swell. So I do not want to expand the numerator. So this is also a lecture on expansion. Sometimes we don't want to expand. So in this case here, the second expression looks nicer. So how do we do this? Well, I will declare the letters x and y as the two variables. I will type in my expression. So another reason to do this rewrite is that one gets a rational expression of this. Now come to think about this of LaTeX, so I have the show. Let me now see if I'm just freewheeling now. So there is also the LaTeX command that you get here. So that could also be a very good way to learn LaTeX, or even a way to automatically generate the LaTeX from the expressions. Okay, so I'm now kind of distracting from the original problem. So, and let me distract a little bit further. So I was talking about the expand. So one could apply the factor. And the factor brings things under common denominator, but it actually does what we don't want. While the factor method brings on the same denominator, it expands the numerator, something we wanted to avoid. So again, our expressions here are very small, but imagine that you deal with very huge expressions and all of a sudden your computer starts to freeze because your random access memory is completely full. So symbolic computation is powerful, but the exponential growth of the size of your expressions might be crippling for your computations. Okay, so this is on substitution. So the substitution in general takes in as input, and I went a little bit too fast, I have to declare another letter. So the substitution takes on input was too fast. So let me type in what I was saying. So the subst method to use in general allows on input a dictionary. So if you have taken Python, then you know what is a dictionary. But here we have the dictionary with curly braces and consists of two parts, where the key, so the first part is what is before the semicolon, where the key is replaced, so will be replaced by the corresponding value, and this is not y, it is z. So you could see, so there's the curly braces. From mathematics, it's kind of suggestive for a set. So a dictionary allows for a very efficient lookup. A typical application of a dictionary in Python is a frequency table. So the language will come up with an efficient storage of the data, efficient for the lookup. So it's a very nice data structure as well. Okay, but I forgot what are we really going to do here is that we're going to bring this under the same common denominator, so as we have done here. But of course, the z is just a temporary variable, so just a placeholder, and I want to have my final expression where I substitute back. I have the r, typed something in too soon, where I have the r, where I'm going to replace the z by x plus y. So the last substitution was a symbolic evaluation. Something that we used symbolic evaluation on general expression to distinguish them from the expressions that we had made for the fast callable objects. Okay, we are halfway in this lecture, so I have done the first part. Let us illustrate the difference between simultaneous and sequential substitution. So what is simultaneous substitution? If we replace everything all at once, then we are performing a simultaneous substitution. If we replace one symbol or expression one after the other, then we are performing a sequential substitution. So this is another way of the definition that we had on the slides. So let me reset everything. So because I'm going to work with a new expression in new variables, A, B, C, and I have the expression A plus 2 times B plus 3 times C. Okay, so you see, even when I'm wanting to be too quick, I make mistakes. So notice that if you are familiar with Python, then you do not find the error messages all that scary. But note that from the name error, you can actually see that I forgot the quotes. Okay, what do we want to do with this? Suppose that we want to replace the A by B, the B by C, and the C by A. So this is what often is called a cyclic permutation. The expression is not invariant under this action, so we will see something different. So there are two ways to do this simultaneously. So I will first show it the long way with the dictionary. So subs the dictionary. So the keys are A, B, and C. The values are B, C, and A. And you see that what happened is that the C became A, so the three A's up front here. The A became B, and the B became C. So one would like to write this 2 plus 2 times C plus 3 times A, but in the order, Sage still has a preference for the A over the B and the C. Writes this in the dictionary order. Now, the faster way to do this is by symbolic evaluation. Now here the two are equivalent because the keys are just simple variables, not expressions. Okay, so the above simplification, substitution, is simultaneous. Now, nothing ever happened actually, so how do we know? Well, let's see the difference with sequential substitution. So doing this sequentially with the dictionaries is first doing the replacement of A by B. So that will give a new expression. So I didn't give it a name previously. I'm not going to give it a name here either. So I'm going to do the second substitution. And then the third substitution. And you see that this gives a 6A. Now, on the slides, I explained why this happened. So if this is rather surprising, please look back to the slides. When we replaced A by B, the B got added to the 2B. When we replaced the B by C, the 3B got added to the 3C, and finally the C got replaced by A. So the 6C became the 6A. So questions like that are you are expected as a result of this course to understand what happened when a command is executed, what the effect is. So the other way of doing this, if I do this with the symbolic evaluation, here I'm just like I apply the dot method. So every time when the dot method is applied, a new object is returned. Here the same. So after the first symbolic evaluation, an object is returned that is callable. So where I apply this evaluation. So both statements are equivalent, again, because we are running this on symbols. So we are replacing with symbols. Okay, let me look at the expansion again. Or I would probably prefer to call this collecting terms in an expression. And here this is again avoiding expansions. So let me describe the problem. So we want to rewrite So a plus b plus c. So let me do this very explicitly. I'm using the star for the multiplication symbol into a plus b plus c without, and perhaps again emphasizing this, without fully expanding the expression or the product. So what is the product? The product is what is given. So this is this star here. So when this, let me type it in, I still have the ABC, and the x is already essentially defined, so I can most likely write down this. So from what I have executed before, if you are beginning from scratch, you do have to declare the A, B, and the C. So here you see that the x is a little bit preferential. The order is different, but the automatic the automatic expansion, or which shouldn't be automatic, the expansion or the computation, if you like, of the product did not happen because of expression swell. So here if you multiply 3 terms by 3 terms, you get 6 terms, which is not, 3 times 3 is 9, I'm sorry, which is not actually exponential, but still, if you then do something more with this expanded form, and these are multivariate forms, if you like. Okay, so I have a lot of time still, so I can take the opportunity to show a little bit more, to show more examples. Let me show the quickest way. So the exercise that I will probably solve, a good exercise is to work with the substitution to a new substitution of a plus b plus c using z. So I will solve this exercise, but let me first say that if you really had to do this, and the quickest way to do this is to see this expression as a polynomial in several variables. So let me introduce this. So the quickest way to collect the terms is to view P as a polynomial in X with integer coefficients, which as coefficients, polynomials in A, B, C with integer coefficients. So saying this, explaining this, takes actually a lot longer than the command that I'm going to type in now. So we have seen multivariate polynomials, and here we see an application of working with multivariate polynomials. So also typecasting. So this polynomial will be cast in a polynomial ring with integer coefficients. So ZZ is the notation predefined known to SageMath for the integer coefficients. I have the letters A, B, and C, which are also predefined. So this is the coefficient field. So as the coefficient or coefficient ring, I'm sorry. So the space of coefficients are all polynomials with letters A, B, C. These are the three variables. The coefficients are integer. The leading variable is x, and I will do the typecast of this polynomial. And there you are. So here we see the desired form. Okay, so let me do the exercise now. So because I still have some time left, so let me do the exercise. So let us do the exercise while I'm doing it. So using the substitution. So in some sense, substitution is a more down-to-earth solution. So I will do this self-contained. So I have to declare the new letter that I'm willing to use. Perhaps let's, for sake of the benefit, use the letter E. So I will make a new expression Q by substituting the expression A plus B plus C by E. So, and that gives me the shortened version. I will expand. So let me expand. And then I will substitute again by the symbolic evaluation. So the E will be replaced by the expression A plus B plus C. So this is the three-step procedure. But if you like, if you use a new letter, there is an extra step there. So this is the longer way to, again, prevent the expression swell. So via substitution of the expression A plus B plus C, in P we prevented expression swell when the expand was applied. So one could say expand you should never do because of expression swell, but if you do it in the right circumstances, after the proper substitutions, the expand is quite harmful here, and as a fact desired as well. Okay, I'm 40 minutes in. So there is the factorization, numeric, symbolic, and exact. Note that this also works over finite fields. And we have seen examples of this. So I come back to this key point here. So let me move the Jupyter notebook a little bit aside. So perhaps I can, I have 10 minutes left. Perhaps let me now illustrate as an extra illustration of the exact numeric and symbolic factorization. So now that we know the expand, I can I can reason geometrically. So let me work with a random root. So I will take a random element. That's not so funny here. So the random element is I actually had expected a little bit. So -7/2 is a lot better. Note that you can set the seed, perhaps to make this really memorable. So this is setting the random seed, and I can use something to code in the date. So this is the year, the month, and the day. See if this is so special now. Well, 1/7 will have to do this. So this will be the rational root of my polynomial. Then I will generate a random factor. So let me say this is the factor, random element, and I want degree is fine, degree 2 is fine. Okay, so this is my random polynomial. Let me see if it's gonna be a good polynomial for what I want to do. So it is an irreducible polynomial. Is it? Is it? It is true. Okay, so what I'm showing also here is how I make my examples for tests and quizzes. So I have my root r and I have the factor. So how do I now make my polynomial? So here is where the question would start. I would take the x minus r times df, and let me expand everything. So here is the question. Compute the numeric, exact, and symbolic computation of P. Okay, so let me do this in a couple of minutes. So the numeric factorization corresponds to the root finding over the complex numbers. Or algebraically, we cast the polynomial into the complex ring. So here you see the roots. I have my so it was 1/7, right? So you can see that the 1/7, well, I'm not used to work with 1/7, but I think that you can probably recognize this here. So we have this real root, and then also there are the other roots there. So this is the numeric factorization. The exact factorization starts from here. And now the symbolic factorization starts from the factors. So I have to take the list of the factors. So we just computed the numeric and exact factorization. So for the symbolic factorization, we must extract the irreducible factor from the exact factorization. Now we know the factor. I constructed it. It is this f that I defined earlier. Oops, I'm so sorry. Okay, so this recording is kind of a little bit messed up now. Let me restart all over. So I'm sorry, so this was a mishap. So what I wanted to do is to illustrate another example of the exact, the numeric and the symbolic factorization. So I started with a random root with the date of today. 1/7 is the root of today, the random root. The irreducible factor is constructed also at random for this day. The f is irreducible. So I want to look at this polynomial then as a given. So you can see, if you want to have more and more practice, you construct polynomials such as yourself, and you can make them as difficult as you like, of high degree of many terms. Here we will have to expand twice. So the problem is that given p, so this is the polynomial computing numeric, exact, and symbolic factorization. So the numeric factorization is executed here with this cast. The exact factorization is the starting point for the symbolic factorization. So what I will do is I will construct a list, capital L. It's never good to use a little l. And I can't really do the list, so let me capture the factor f. And let me see if I can do that. Okay, perhaps I should not improvise. So I have the factor object. So I can get to the operands. That will give me the factor as well. So, and it comes up right up front. Okay, so I will now make my field extension. So I will extend Q using the letter. What would be a good letter for, let me now use alpha, because I have used A before. So I'm going to extend the rational number field with the root of the irreducible polynomial. So once you have your irreducible factor, you are actually ready to define the field, and then the symbolic factorization is another typecast. So I have my field Q2. I'm going to cast the polynomial into that new field. So the polynomial was P, and I will factor it. And there it is, the symbolic factorization. Where you can read off the 1/7, and you can read off the two symbolic roots alpha. So all the numbers minus alpha and alpha. So this is the symbolic factorization. So I hope this lecture was interesting, and I'm sorry about the detours and the mishaps, but you see that I still finish in time with what I wanted to show.